All right, our problem is figuring out the z-scores. Now, it's not that big a deal. The idea is that if you tell me something, anything is normally distributed, then what I need to know is its mean and its standard deviation, and then I know everything about its distribution. And if you have two things or more that are all distributed normally, they have normal distributions, they have bell curve distributions, though there are other distributions that look bellish, then I know how to draw each one, and I'll show you. But more importantly, I know how to translate them all to the same normal distribution. It turns out that translating any normal distribution to the standard normal distribution, to the normal distribution that has mean right at 0 and standard deviation 1, that's pretty straightforward. And I'll show you an example of why we want to do that. But first, let's see the transformation, okay? So I've got some pictures here. So different standard deviations, different means, all normal. So look what we have here. I've got a picture of three normal distributions. One has a mean of -3, one has a mean of 2, and one has a mean of 12. But not just that, you'll see some are really spread out. Remember, all of these have area, the information is in the area. All of them have area spread out more or less than the other. The standard deviation of this distribution, the orange distribution, is 1/2. The standard deviation of the green distribution, or this distribution 3, x3 here, for x3, is 2. And this distribution of this really flat one has a standard deviation of 5. Okay, now what I'd like to do is show you how I'm going to transform all three of these to the standard normal distribution. Well, first thing I want to do is slide all those means to 0. And how do I do that? Well, translation in algebra is just by subtraction. So I'm going to subtract the mean from each of these distributions and force them to go to 0. Now notice one mean is negative, the other two means are positive. And yes, you have to think about the fact that when you subtract a negative, you get a positive. All right, let's take a look at that picture. So here we go. I have in a very faint outline the old distributions. But now I've translated them all to line up at 0. But how do we do that? How do we do that? Well, this picture should tell you how. So to get the orange distribution, which had a mean at 12, I think of all the values on that distribution, all the values along the x-axis, I should say, subtract 12 from it. And that shoves the whole distribution, all that probability sand, over to 0. For this distribution, I take x3, and for all the values, I subtract -3, which shoves it over from the left to 0. And in this really flat normal distribution, I take all the values and subtract 2. And that moves it over 2 spots, and now all these values that are represented by this distribution have mean 0. Okay? Now, if you look on this picture, I now explicitly tell you what the standard deviation is for each of these. So standard deviation 12, standard deviation 2, standard deviation 5. So what I want to do is either stretch out or squeeze in, and in two cases I want to squeeze in, and in one case I want to stretch out all of these distributions to have the same shape as the standard normal distribution, which means standard deviation 1. Now, how do you think you do stretching? Well, if you remember back to when you first were learning about addition, which does translation, multiplication was the thing that did stretching. And multiplication, and in our case, it's division that we want. So what I want to do is divide these values by the standard deviation. And that forces the standard deviation to go from being whatever it is, one of these three standard deviations, to a standard deviation of 1. So let's see here. So faintly drawn are the three former standard deviations, normal distributions, and then in red here is the standard normal distribution with standard deviation 1. And so what I did is for the first one, I took all the values that were translated by 2, I divide by 5, the standard deviation 5. In the second one, I took all the values that were translated by 12 and divided by 1/2, the standard deviation 1/2. And I took all the values that were translated by -3 and divided by 2. Each of those actions turn each of these 3 distributions that are lightly outlined to the normal distribution. And what it does, this is the key here. What it does is it takes any normal distribution values and it turns those numbers, x minus the mean over the standard deviation, x minus the mean over the standard deviation, turns it into something what we call a z-score. And the z-score tells me how many standard deviations from the mean that value is. And I'm going to give you an example, though I imagine Dr. Taylor's going to do a few. So take the following example. A classic example, and I've already used it once, is heights. Heights tend to be bell curvish and so normally distributed. So suppose we have that the height of males in the U.S. has a mean of 70 inches and a standard deviation of 4 inches. So, and is normally distributed. And females have a smaller mean, but also a smaller standard deviation, so there's less variance. And here's my question. What is more extreme? A 6-foot female, so a female who is as tall as I am, or a 6'6" female? And I guess I'm more like 6'5" now, but there was a time I was 6'6". A 6'6" female or a 7'1" male. What is more extreme? Well, it's certainly the case that 7'1" is taller than 6'6" inches. But my question is more subtle. Which is less likely to happen? If I go out and see some people on the street, what am I less likely to see? A 6'6" or taller female, or a 7'1" or taller male? Now I'll point out that the difference between these two is 7 inches to get from 6'6" to 7.1, but the difference in the means is only 5 inches. So you might be tempted to say, no, the 7'1" male is actually more extreme than the 6'6" female, but what you're not taking into account is standard deviation. And that's why we need z-scores. So let's transform each of these into their z-scores. So how do I do that? Well, here I take the 6'6" and translate it into, translate it into inches. So that's 78 inches. And I hope I did the math on that right. If I didn't, y'all can laugh about that later. So it's 6 times 12 is 72, plus 6 is 78. Okay, now the z-score. So I translate that value. I take 78 minus 65, and that tells me how many inches from the mean I am for females. And then I divide by 3.5, the standard deviation for females, and that tells me 3.71. That's the z-score for 78 inches under the normal distribution for female height. And that's 3.7 standard deviations from the mean. And we know something about that. That's very unlikely. That's way in the 99.99 range. Okay? Now, let's transform the other one, see what we get. So the other one is 7 foot 1 inch. That's 85 inches. 7 times 12 is 70. 84 plus 1 is 85. I think I did that right. Oh, wait a minute. 84, 85. Yeah, I think I did that right. And then I subtract 70 inches, the mean height of males. So that gives me what? 11 divided by 4. That's 2.75. That's very unlikely. It's very extreme. But look, that 6'6" female or taller is 3.71 standard deviations from the mean. Very unlikely. Small probability of that happening. Small. Why? Because a very small portion of the population have that, are female and have that height or higher. While 2.75 is nothing to sneeze at, it's not as extreme. There is a greater population of males in the U.S. that have that height or higher. So that's how these z-scores, that's how you compute them. And that's how one way of using them to compare to each other. We'll actually use them over and over again. It's just a matter of a subtraction and a division. Just use your calculator. There are ways of doing the stat crunch, but you don't need anything fancy. subtraction, then division. Okay? See you in class.